In this video, we're going to talk about circles and some different angles things. So mostly central angles and inscribed angles. Before we do, I wanted a quick refresh on arcs. So when we talk about an arc, it just means a piece of a circle. A minor arc is when it's less than 180 degrees. A major arc is when it's over 180. And if it's exactly 180 degrees or half the circle, we call it a semicircle. And so, again, an arc is just like part of a circle that's created, like a windshield wiper's path as it goes across your windshield. We'll eventually talk about the actual length of these arcs. So like if I were to like get a tape measure and kind of curl it and measure the length, we'll talk about that later. What we're going to talk about today is the angle measure of the arc. And the way you find these is it literally just matches the central angle. So what I mean by that is, let's say this central angle here is 70 degrees, then the arc is also 70 degrees. So the measure of the arc matches the measure of the central angle. The measure of this angle right here would be the same as the measure of arc Cd. Keep in mind all circles are 360 degrees. Like if I went all the way around 360, that would be a full circle. So that means the entire arc, like all of this added up, should also be 360 degrees. Let's do a few examples real quick. So if you put a little m in front, that means the measure of. So what's the measure of arc HJ? HJ is right here, so it goes with that central angle. It's 63 degrees. This is the measure of FGJ. So FGJ is this semicircle. It's on a diameter, and that's always 180 degrees. So I know that FGJ, all the way around half the circle, should be 180 degrees. It's half of the full 360. And then the measure of arc FGH. So this arc here. To find that, I need to know the central angle FKH. And I know that this piece is 65, but I don't know this piece. But I can solve for this piece because I know that the entire thing is supposed to be 180. So basically just subtract those two from 180 and see what you get. So 180 minus 65 minus 63 leaves you with 52 degrees. So all of this adds up to 180. And if I just want this arc, or this angle, add those up. And so 65 plus 52 is 117. Here's another example. Say I want to find the measure of arc CDE. So CDE. I know that this is 90, so that CD is 90, but I don't know what DE is. However, these two angles right here are vertical angles, and we know that vertical angles are always the same. So if that's 40, this is 40, meaning if the central angle is 40, the arc is 40. So if I want all of this, just add up 90 plus 40, and you get 130 degrees. If I want arc BCD, so here, BCD, again, I'll add up that 90 plus whatever this is. This is another one where I don't know exactly what that is, but I know the whole thing is 180. So one way, and we could have done this on the last one too, if I know from D to A is 180, basically just take out the 40. Just do 180 minus the 40 degrees, and you get 140 left for this piece. 140. If you wanted, you could have solved for this individually. It would have been 50 and then add it to the 90, and you get 140 that way as well. But all right, let's try another one. Measure of arc Lmn. So right here. Let's see. Again, this is one where I know that this entire thing is 180. So subtract the 105, and you would get just 75 for this piece. And then LNP, so LNP figure out what this little piece is. So it's 180 degrees plus whatever this little piece is. And to find this little piece, let's go back to what we were talking about before. I know that this entire thing is 180. So to figure out this, subtract this and this from 180. So do 180 minus 30 minus 105, and that leaves 45 degrees for this little piece. So if I have 180 plus an additional 45, that would be 225, which makes sense because that's over half the circle. And one more example, the measure of arc AB is just 90 degrees. ACB is 360 minus that, so it's 270 degrees. Because together those have to add up to 360. All right, here's a little multiple choice kind of question. The measure of arc CEA. On this one, there's a few ways to do this as well, but I would do it as like this piece is 180 because it's half a circle. Anytime you can figure out if something's half a circle, that's helpful. And then just add an additional 20. So 180 plus that 20 would be 200. I'm going to skip over these. All right, now let's talk about inscribed angles. So far we've talked about central angles, which are at the center of the circle. But what about inscribed angles, which have their vertex on the edge of the circle? With inscribed angles, do you think this is always, sometimes, or never true? An inscribed angle that has the same arc as a central angle, like this, they're on the same arc, will always be smaller than the central angle. Do you think A will always be smaller than B, basically? The answer is true, and how much smaller do you think it is? Like, for example, if B were like 40 degrees, what do you think A would be? Just kind of as a guess. So it turns out, and you could get a protractor and measure if you wanted, it turns out it's always exactly half. So notice this arc here is 54 degrees, and that's 27. This arc here is 160, that's 80. So the inscribed angle is always half the measure of the arc, which means it's also half the central angle because the central angle and the arc are the same. But this is always half of this. Same thing here. If this is 90, then the arc is 90, whoops, which means half of that would be 45. All right, so for example, find the measure of angle BAC, so this right here. Again, it's just half of that. 126 cut in half would be 63. Find the measure of these missing arcs. So if that's 48, double it to get the arc. So that would be 80, 96. Or on this one you're gonna have to do a little work because I don't know what that angle is, but I know a full triangle should be 180. So do 180 minus 63 minus 37, you get 80, and then double it, and that will give you this, which is 160. On this one, the measure of arc XZ, I know that one looks kind of complicated because of the whole polygon happening in here, but it's still just double this, because this angle subtends that arc, it goes with that arc. And so you still just double the 66. What is that, 130? Just want to check. 132 degrees. Let's do kind of a complicated one here. We'll come back to that. You may have to do some algebra with this. So for example, if I want to find the value of x, I know that this thing doubled gives me 96. So there's a couple ways you could do it. You could do this times 2 and say that equals 96. Or you could say 2x plus 1 equals half of 96, which is 48. And then just solve for x. which is 23.5. All right. On this one, you know that if you doubled this, it would give you that arc. So this times 2. And you know if you doubled this, it would give you that arc. And all together, that should equal 180 because it's half a circle. So if you add that together, it should equal 180 degrees. So solve that equation for x, and that would be how you work that one out. Kind of trying to skip through these here. One that's similar that I wanted to mention, this is not an inscribed angle, but it's very similar to an inscribed angle. It still has its vertex on the circle, but it's not two chords. It's actually made out of a tangent and a chord. And so these are literally called tangent chord angles. Still, it has its vertex on the circle just like an inscribed angle. And so the same rule actually applies. Whatever this arc is that it kind of cuts out, that angle is always half of this. So if that's 120, this is going to be 60 degrees. That angle, the red angle there, formed by the tangent line in a chord. Here's another example. Let's say this angle right here is 56 degrees. Then if I wanted that arc, AB, I would just double it. So 56 doubled would be 112. All right, and then there's a few other things we can do with these inscribed angles that I wanted to just hit on. One is called the Bowtie Theorem. So notice this angle right here intercepts arc AC. See how it hits at A and C? This angle right here also intercepts AC. They're on the same arc. And so, like, let's say this were 40 degrees. I would double it to get the arc, and the arc would be 80. And then to get from this one to the arc, it would also be doubled. So this would also have to be 40 degrees to double it and get 80. So basically, if you have multiple angles that are on the same arc, they're always the same. So these two are the same, and in fact, these two would also be the same because they're on arc BD. I call this the Bowtie Theorem. I don't think that's an official name or anything, but basically it says two inscribed angles are going to be congruent if they're on the same arc. For example, if I want to find angle CBX, where is that? CBX, so that right there. I know that CBX is the same as angle A here. So if I want to find it, and I also know if that's 32, then this is 32 degrees. And so now I can just do the triangle thing. They should add up to 180. So do 180 minus those two. And you get 63. So that's my answer. Another way to do it would have been, those are vertical angles, so this is also 85 degrees, and then you could have figured that one out, and you know that those are the same as well. So either way. So that's the Bowtie theorem. Basically, these are the same and these are the same because it looks like a bow tie. All right, what do you think the measure of angle MTE is right here? What does it look like to you? All right, we can use our inscribed angle stuff here. MTE is on the arc ME. And what is the measure of ME? Well, since it's on a diameter, it's exactly 180 degrees. I know for a fact that's half a circle. And so using the same rules from before, if I half that, this should be 90 degrees, which is a right angle. So this is kind of an important theorem. It basically says, anytime you've got an inscribed angle right on a diameter, like this, see how it's on the diameter? It's always a right angle because it's 180 cut in half. Same thing here, 180 cut in half is 90. So any inscribed angle, even if it's kind of sideways on a diameter, is going to be 90 degrees. So for example, what is MNP? there's a lot going on here and I don't need any of it. MNP is on a diameter, so I know it's 90. That's it. Or for example, what's angle X? To find angle X, it would help to have this angle, and I do know this angle. Again, since it's on a diameter, I know it's 90. And so do 180 minus 90 minus 37, or just 90 minus 37, and you get 53. So there we go. By the way, inscribed polygons are just combinations of inscribed angles. So all the vertices lie in a circle. All of these are inscribed angles. That's an inscribed angle, that's an inscribed angle, and so on. This would be an inscribed pentagon. Remember, we actually did some of these constructions. We did an inscribed triangle, we did an inscribed square. What I want to focus on is inscribed quadrilaterals, which would be made out of 4 inscribed angles. So with inscribed quadrilaterals, the opposite angles are always supplementary. The opposite angles always add to 180. So like A and C should add up to 180, and B and D should add up to 180. This doesn't happen with all quadrilaterals, but it does if they're inscribed in a circle. And just to do a quick proof of this, the reason being, like, let's look at angle C. Angle C is on this arc, and angle A, right here, is on this arc. I know that those two arcs added together are 360 degrees. It's the full circle. And so I don't know exactly what A and C are, but I know they're inscribed angles, and so to find their measure, I would cut the arc in half, and I would cut this arc in half. So basically, if this is the sum of their arcs, then this is the sum of their inscribed angles, which is 180. So again, I don't know exactly what they are, but I know that these two together should be half of this, 180. For example, let's find the measure of each angle in this quadrilateral. So I don't know anything about that angle yet, but I know that these two should be the same, because, oh sorry, not the same, should add up to 180 because it's an inscribed quadrilateral. So basically just add these up and set it equal to 180. So just do a little algebra here. That's 12, and so that's 7x plus 12. And then subtract 12 from both sides. You would get 168, and then divide by 7 on both sides. You'd get 24. That's not the answer, that's just x. So to find the actual measures of the angles, I'd put this in for x. So 24 plus 17, which would be 30, 41. And to find this one, you could either put in 24 for x, or just do 180 minus this. So 180 minus 41 is 139. Also, I could put in x here, so put in 24 again. So 48 plus 19 is 67 degrees. And then again, to find this one, just take that, but minus 180. So do 180 minus the 67, and we get, well, it's 113. So those are all the angle measures. By the way, total, it should add up to 360, because you've got 180 plus 180, so it should be a total of 360. All right, that is all the inscribed angle stuff.